So in this next section, I'm going to talk about some additional electrical devices that we can create in IC chips and how they're typically created. So the first of those is creating capacitors. So one thing to note is, we do have a capacitance that is our gate capacitor for our transistors, the metal oxide semiconductor capacitor. The key thing to note with that is, as we're creating the channel, that capacitance value is actually nonlinear, because before we create the channel, we have a certain capacitance that doesn't really follow a normal linear capacitance. So using the MOS device of the transistor as a capacitor isn't necessarily the most ideal to get a nice stable capacitance value. So instead, one of the things that we can do is we can always use from one metal layer to another, we could create a parallel plate capacitor. The problem is, from one metal layer to another, typically we try the processing technology, we try to create a thick oxide layer between metal layers because we're trying to reduce the capacitance between metal layers as much as possible to increase our performance. So generally, there's a thick oxide between layers, and the metal parallel plate capacitor is a fairly low capacitance, so it doesn't work very often. So the best option to use is using a single metal layer. We can take and do an interdigitated fingers of a single metal layer. Especially in the lower metal layers, we have the spacing between one metal line and the next neighboring metal line. In order to have a decent increase in density of the number of metal lines we can have, we have a fairly tall, or the space between metal lines compared to the height of the metal line tends to give us a good ratio to get some capacitance out of that. This is sometimes called a fringe cap or a metal finger cap. Now this will, because this is a linear capacitance, it will behave linearly with voltage. So we get a predictable linear cap behavior, and the value that you put on the voltage for VA and VB can be any value basically, as long as it's not above the value that would cause the oxide to break down. So you're not required to have the value be like one of the terminals be VCC or one of the terminals be ground, like you would if you used a PN junction for a cap, where one of them would have, you need to make sure one is always higher than the other. So this allows you to have a predictable linear cap behavior that you can assign to whatever voltage for each terminal. Another common circuit element, of course, is a resistor, and there's a few different ways that we can create resistors. First of all, we could create resistors using diffusion layers. This can give us a high resistance, but the problem is we also get a high capacitance because our diffusion layer is a PN junction. So we need to create a reverse bias PN junction. And in addition, because you have a reverse bias PN junction, you get leakage currents. So usually the leakage current that you get usually is somewhat unsuitable for having at least high precision resistors, and you have current going in areas that you don't want it to go. So typically that isn't used very often anymore. So another way is to use polylayers for higher resistance rather than metal layers. But a lot of times, as I mentioned before, your polylayers are silicided along the top of the polylayer in order to lower the resistivity. So you might not get quite as much resistance as you really want to out of your polylayers. So one of the ways that you can solve that is if you can use an additional blocking mask that you can define over areas where you don't want your poly layer to be silicided. So specifically you use this blocking mask over areas in analog where you're trying to create resistors, and that allows you to get more undoped high resistivity poly. So you can sometimes tune your resistivity to maybe up to 300 to 1,000 ohms per square, which means you can get a relatively high resistance by doing this type of thing. And then if you have a like an unsilicided poly layer that you've created, then you can use what's called a meander structure in order to you can create a finger of poly or whatever layer you're using to create a unit resistance. So you have a one finger of that layer gives you 1 unit length worth of resistance, and then you can connect multiple fingers in series to create X times whatever that unit length is. So typically the figure below shows that type of meander structure just for basically 3 fingers worth. Typically what winds up happening is in analog areas, if you're creating structures that have a certain look to them, you'll create some dummy fingers on either side of the overall structure. That way you don't get different behavior from the very edge fingers versus the ones in the middle, because all of them see the same look to the left and right of each finger, and so all of them behave more similarly if you create some additional dummy fingers that you don't use on the outside. So this is the typical way of creating resistors on IC chips. And then of course one of the next circuit elements that is commonly needed but maybe a little bit less often than resistors and capacitors is inductors. Typically your inductor will be formed on your topmost thickest metal layer as a spiral, because the inductance value is going to be a function of how much area and how many spiral windings you have around that area in the middle of the inductor. And being on the topmost thickest layer, you want that in part because you want to reduce your parasitic components as much as possible. One of those parasitic components is the series resistance. So having a thick metal layer that is also wide can reduce the resistance of the inductor, the series resistance. Then you'll also have a parallel capacitance to ground, so the capacitance between the inductor windings and a metal layer above or below that if it's the topmost metal layer, then you won't have another metal layer above it. You will have some capacitance to the layer below it, but then you also have the shunt capacitance, or capacitance between successive windings. So again, being the topmost metal layer, it's thick, but it also has a wider space between windings to reduce your capacitance values. Another thing that is sometimes needed on some specialized integrated circuits are transmission lines. The figure below shows a couple different types of transmission lines that can be formed. One type is the microstrip, as shown in the figure A, where you have a line that's formed with a very specific width, specific thickness, and a specific distance, the H, between the microstrip and the ground plane underneath it, and so that's the microstrip type transmission line. For the coplanar waveguide, you'll, in addition to having a specific line width and space, you'll, instead of having a distance from a ground plane on a separate metal layer, you'll have a distance to the ground lines next to it. So a certain spacing between the line that you're driving the signal on and ground lines on either side of it. So the design you use will be based on your desired frequency of operation and other factors, but transmission lines are used for certain types of functionality. Now it turns out that we can also use the traditional CMOS process not only to make NMOS and PMOS transistors, but we can also make bipolar junction transistors, or BJTs. And if you do this in a traditional, like you create a traditional CMOS process to create BJTs, it's typically called a bi-CMOS process. And below there's a figure showing how we can do this. So if we have a P substrate with an N well, in effect the cross section you can see on the left, we use, instead of creating a P plus and then N well and another P plus to create a PNP transistor, we use the P plus diffusion as an emitter of a PNP BJT. So the P plus diffusion is the emitter, the N well is the base, and we use our well connection, or N plus in the base, as our base connection. And then the P substrate is the collector for a PNP transistor. And so that's the way you can create a PNP transistor. On the right side, it's showing how, from the top view, how you would actually create it. So rather than just having a single contact on one side of the well, you actually want your collector, because the current, you want your collector to have as low a resistance as possible in order to go between the emitter, base, and collector. So you want the collector completely surrounding the base, and you want to have a good number of contacts to your collector, good number of contacts to your base, and then you have your emitter, basically one central contact in the middle. Depending on exactly how much resistance you want, you could have your emitter slightly bigger and maybe have 4 contacts or something, but depending on the performance you want from your transistor, you can vary your layout a little bit. Now, if you want an NPN transistor, you can use a triple well process to get in to do a similar thing to create an NPN transistor. Or you could use your N plus active area as an emitter. You could use a P substrate as your base, and then an N plus active area as your collector to create a kind of horizontal NPN device rather than doing a vertical emitter to base to collector, as shown below. The problem with that, though, is if you use N plus as emitter, P substrate as base, and N plus as a collector, you don't get a very good beta out of that. So it's actually kind of a not very good NPN transistor. So not as recommended as using a triple well process to do an NPN BJT. So one additional circuit element that's very useful in IC circuits is what's called non-volatile memory. So non-volatile memory is a transistor that will retain state once power is removed. So the simplest way of doing non-volatile memory is something that's a read-only memory. So you program it as you're creating your masks in your initial design. You program whether this is on or off, so a transistor is on or off, and it's non-programmable after you actually manufacture your chips. So So it's something where you program it to a certain value, you always want it to be that value. But from one design, if you find there's a problem, you can quickly change maybe a metal mask, like a single metal mask, and start producing new chips in the fab that you reprogram it just through changing one single metal device in your mask early on in the process step. A different way of doing non-volatile memory is a one-time programmable, or OTP, where you could have a device that has a thin metal fuse. You can vaporize that fuse with a high current, and then you have a value that you can read out. But you can't change that value after you've programmed it the first time. Something that's come into play more recently and is kind of the most useful non-volatile memory that we currently use is flash memory. And so this uses, it's shown in the figure below, where you effectively have a floating gate on top of a thin tunnel oxide. So instead of having your normal gate oxide over your channel, you have a really thin, much thinner than normal gate oxide that's called a tunnel oxide. And then you have a gate on top of that that isn't connected to anything, so it's floating. And then above that is your control gate on top. You have a gate oxide on top of the floating gate, and then control gate on top. So what you can do is you can program this cell by taking your control gate on the top of the cell and bring it to a very high control gate voltage. This high voltage will cause your floating gate to get pulled up, and as that gets pulled up to a higher voltage, there's the thin tunnel oxide under that floating gate can actually allow carriers to tunnel through it, and the floating gate gets basically charged up or discharged depending on what you did with your control gate, whether you put a high voltage or a low voltage there. And so electrons can tunnel into the floating gate from the bulk. And this causes that floating gate to now have an artificial charge on it that will stay there even when power disappears from the circuit. So this floating gate is now at a certain charge even when the control gate goes back to ground. And that charge will cause the channel to be either on or off. So when you program the cell, you pull charge into the floating gate, and then that floating gate will cause the channel to be charged and to be on all the time, even when the control gate voltage goes away. And then you can deprogram the gate by raising the bulk voltage really high, and the control gate stays low, and then the bulk will pull the electrons out of the floating gate, and then the device will always be turned off once the control gate and the bulk go back to normal. So the one thing to note about the flash memory is the source and drain of the NMOS device actually are different. Normally our source and drain of like an NMOS or a PMOS are identical to each other when you're constructing it. But in this case, your source and drain are different voltages because you need to make sure that the drain of the device will withstand the high voltage levels needed by the programming of the floating gate. So just an additional note about how the construction of flash memory happens. So fuses are another circuit element that are used commonly in integrated circuit chips. They're used for various different reasons, but the main thing is you want to program a certain value once. Generally it's done after you do manufacturing, but before you ship parts. You will do some testing on a given circuit. You might program in a codes saying what this chip is, what the serial number is, etc. There's other various things that as you're testing the chip, you might say, oh, this chip works at a certain frequency and a certain voltage, and so you program those values in to the chip before you send it out. So there's a number of different types of fuses that you can use. One type of fuse is you have a narrow metal wire. You pass a high current through it, and passing the high current will blow the fuse. You can, instead of passing current through the wire, you can maybe have a narrow metal wire where you zap it with a laser to blow the fuse. You have to be careful doing that sometimes, though, because I've actually seen where we've done that when I was in debug. We would zap a wire with a laser, and it could actually cause the metal to kind of boil, if you will, and it boils hot enough that it maybe splatters in effect, and it can blow onto neighboring metal wires and wind up causing shorts or damaging circuits nearby. Another thing is, if you're not using metal, if you're using poly as your fuse, if you pass high current through it, you can, instead of blowing the fuse, you're damaging the poly and increasing the resistance, and for example by an order of magnitude, and then later on you can measure the resistance value to determine whether it's a high resistance or a lower resistance, in order to determine whether it's quote-unquote a 1 or a 0. And they also sometimes have anti-fuses. So it's a device that initially has a high resistance to it, and you can do something where when you program, put a voltage across it, it actually lowers the resistance when you add the programming voltage to it. So just a couple different types of fuses. So below is just showing an example from IBM of what they call an E-fuse. Just showing basically they have on the left is an intact poly wire that's silicided with cobalt and has approximately 200 ohms of resistance through it. On the right, they sent basically 10 to 15 milliamps for about 200 microseconds through it. The cobalt in the polysilicon will migrate toward the anode, and it doesn't destroy the device, doesn't cause something to blow, but because the cobalt is migrating, the resistance of the polysilicon goes up by an order of magnitude, so it goes from about 200 ohms to 2 kiloohms. And you can kind of see a little reaction there, the difference between the two graphs, where you can kind of optically see what's happened, but on the chip they would just measure the resistance difference. Now, going beyond traditional integrated circuits, some things that are being done and have been done for at least the last 20 years with using normal CMOS process techniques is what's called MEMS type devices. And these are micro electromechanical systems. And effectively it's making kind of 3D type structures, sometimes things that actually move. Electromechanical, the mechanical part is things that are moving on the chip. So creating tiny mechanical systems on a chip. These have been used for many years for accelerometers, where you create basically an air bridge capacitor that as it moves, you can the capacitor, because it has an air bridge, will have a little bit of bending, and the capacitance value changes with movement. It's been used for many years in digital light projectors, creating micro mirrors that are on hinges, so really tiny mirrors on really tiny hinges. And if you add you have an array of those, so like if you have a 1080p type display, Each pixel has its own little micro mirror. If you put a electrical voltage, the mirror will either shine in the direction where the light is going on or the light is going off, and they can basically rotate or that mirror at a given frequency to modulate the intensity of the light, for example. Creating mechanical resonators, cantilevers, micromotors. The figure below is showing a resonating MEMS microlever. So you can kind of see on the very bottom where the lever is connected to kind of a T-like structure at the bottom, and you can see as you go up from the bottom T, it gets a little fuzzier because this is a still picture, but it's showing something that's resonating, so you see this fuzzy area where the cantilever is resonating back and forth. So just some really cool stuff that I've seen constructed with MEMS. So CMOS process has also done some integration of photonics, and at least in some like high-speed networks, photonics is replacing copper wires in some applications, and in using normal CMOS process, we're able to develop waveguides, modulators, and photodetectors. The figure below is showing an optical waveguide and holographic lens integrated into a 130 nanometer CMOS process. Now, it's still not something that's really common, but it's definitely integrating photonics is very desirable in normal CMOS process technology because wires have resistance, whereas light, it obviously can go much faster. You don't need to worry about the resistance effects. The main thing is you need to be able to transmit in light and then convert back to electronics in order to manipulate your transistors and go through your transistor logic. But at least for longer distances and really high speeds, photonics can definitely be useful. Now, after we've created a given silicon IC chip, we can do what's called 3D integration of circuits. So in effect, we can take two silicon chips and combine them together to create an additional functionality. So if we can put some of our logic on one chip and some of our logic on another chip, the way that we can do this is typically we have the substrate that our wafers are on is pretty large thickness in order to withstand all the processing steps, and the fact that it's on a wafer that's 300 millimeters, or basically about a foot diameter, it needs to be a very thick wafer in order to go through all the processing and temperature cycling steps, etc. But after we cut out all of our chips, we can grind that wafer down such that the substrate is very thin. So as thin as basically 20 microns worth of thickness. Then we can etch through silicon vias, basically what they call TSV. So through silicon vias. So we etch a via through the 20 microns worth of thickness of silicon through the bottom of the substrate, and then we can create vias that connect the top of one silicon chip to the bottom of another silicon chip, and be able to, so as long as we've designed our silicon chips in such a way that the bottom layers of metal of one chip, we create these specialized pads that we're going to connect to these through silicon vias to the top of the other silicon chip, then in effect we have a landing pad at the top of one chip and a via connection pad for the TSV vias on the bottom of a different chip. And the figure below kind of shows that. So you can see the area that's circled in the middle where they have the 3D via. In effect, those two vias are burrowing through the bottom of the quote-unquote top wafer in order to make connections to the circuits in one chip to the top layer landing pad of circuits in the bottom wafer or a bottom chip. So it's one way that's currently being used to try and bond two chips together in order to get higher density in a smaller area. So there's obviously some potential problems with this, and it increases your number of steps to get a full integrated circuit out. It also runs into some problems with thermal cooling. You now have two chips on top of each other that might just have a single heat exchanger trying to pull heat off of it. So there's various different pluses and minuses, but it's an interesting idea that you might see more of in the coming future. So one of the biggest process enhancements to silicon CMOS process in the last few years has been the FinFET transistor. So up until now, whenever I've shown a MOS device, it's always been you have the silicon surface of a wafer and the N+ diffusion, the channel, and the N+ diffusion for an NPN transistor are all at the surface of the wafer, and it's a flat silicon surface. The advent of the FinFET transistor actually causes the source, gate, and drain to become 3D and come up vertically from the substrate. So you can see in the figure below where we have the substrate, and then we have a source region that comes up from the substrate. We have a thin fin, basically, of a wall, if you will, going between the source and the drain that's fairly thin, and that's going to be our gate region or channel between the source and drain. And what happens is the gate oxide wraps around three sides of the channel. So that channel going between the source and drain is this 3D fin device where the gate is wrapping around it. So the B area of the figure shows a cross section of the gate where we have the source and drain are kind of on either side of what we're seeing here, either side of this cross section kind of going into the screen and on the outside of the screen. The gate oxide wraps around the channel. So three sides of the channel, we have the gate oxide wrapped around both sides and the top of the channel. And then the gate wraps around the channel as well. So this gives us much greater control over the charge in the channel because we now are pushing charge across both sides of a very, very narrow channel there. And so we can turn the FinFET both on and off more fully. So we can get greater on current and we can get smaller off current. And in this case, the device width, so when we're talking about the width of a MOS device, typically we can make it wider or narrower depending on how wide we make the active region. In this case, the fin is a given height, and that height is predetermined. and the width of the channel is defined by the height of the fin. So when you're making a FinFET, you can't just make whatever width channel you want. You get a given width of the channel is a integer multiple of the fin size. So if you make one FinFET, you have a width that is one fin. If you want 2 times that width, you have to take 2 different transistors and connect them in parallel, and then you have an effective transistor width that's 2 times a single fin. So if you want a wider and wider transistor, you have to just put more and more transistors, more and more fins in parallel with each other and connect them all, the sources together, all the drains together, and all the gates together to create X times the width. So this figure here is just showing an actual FinFET design actually fabricated. So this is an Intel FinFET design. Intel calls this a tri-gate transistor. The reason why they call it tri-gate is because you have the gate is formed on either side of the fin and on the top of the fin, and you get slightly different effects because of the fact that you have at the top of the fin you have the corner between the top and the side of the fin, and at that corner your electric field behaves a little differently. So you don't just have a single electric field across the entire channel, but you get slightly different electric field as it wraps around the fin of the transistor. And so they call it a tri-gate transistor. You can see these look much more fragile, much more complex than your traditional flat transistor. So it did take a lot of work to get these actually functional and working correctly. So very interesting design, and the fact that we can make billions of these on a single IC chip and get them all to work is pretty astounding. So one last type of circuit element that I'll mention is basically what's called a carbon nanotube transistor. This is basically you create cylinders with very small, just a few nanometers diameter, which are basically smaller than current gate lengths that we have for traditional silicon or even the FinFET designs. And these nanotubes offer very high mobility, but currently they're still not manufacturable in the same way that we can for silicon CMOS. So to create these carbon nanotubes at the sizes that we currently have for silicon devices, they're still working on creating this type of carbon nanotube. So these are in kind of in research phases right now to see if eventually they might replace silicon, but at the moment they're still not at a point in manufacturability where they'd be able to replace our traditional silicon processing.